In this video, I will show you how to set up robotic production in TaniqWind Pro. During the video, I will be demonstrating the full process of setting up the robotic production of the shown pressure vessel design. This pressure vessel design has 3 layers with helical paths in the first and third layers and hoop paths in the second layer. For the production, we will move into the production tab, which has production, machine path, trajectory, collision, and machine file sections. We will start in the production section at the machine selection button, where we can select a machine from the machine library we want to use to produce this product. For this demonstration, I will be using the Scorpo Leo 1 robot, which is one of the machines delivered by Taniq. If you want to know more about defining your machines, you can find this information in the robotic machine definition video. If we press the mandrel button, we can set the actual offset of the product in the machine. For this demonstration, I will set the actual offset to be 3250, which sets the product in the middle of the axis. By setting the actual offset and pressing enter, we can see the product move in the visualization of the robot. By pressing the OK button, we can set the actual offset to the file. By pressing the settings button, we can open the production settings panel. If you want to know more about setting and using production settings for your production, these are explained in the production settings video. If you press the check button, we can check the connectivity of the paths in the design. Here we can see if the start z-coordinate and winding angle of a path match the end z-coordinate and winding angle of the previous path. If the boxes are not ticked, the paths do not have perfect path connectivity. This can be resolved by adding transition paths in the design. Now we can move to the machine path section of the production tab. In here, we can generate the paths a machine would have to make around a stationary mandrel to apply the material in the designed paths. We can start with setting the machine path parameters by pressing the parameters button. In the machine path parameters panel, we can see 3 sections: a path contour section, a settings section, and a point filtering section. In the path contour section, the contour of the machine path can be specified. The software allows for an open contour, which is a line parallel to the z-axis, an enveloped regular contour, which follows the shape of the profile, a fixed fiber length contour, which keeps the distance between the TCP and the mandrel constant, a continuous tension contour, which will avoid slack in the material during winding for systems which cannot take back in material like wet winding, a placement contour for AFP, and the software has the option to loading custom path contours by some file types like DXF. In the settings section, we can specify the winding distance for the first 4 contour options. For this demonstration, I will be using a continuous tension path contour with a winding distance of 100 mm. In the point filtering section, we can select to use machine path point filtering, and we can set filtering parameters, which can be set such that less points are sent to the machine while a certain accuracy is maintained. With all these settings in the panel set, we can set them by pressing the OK button. Now we can press the compute button in the machine path section of the production tab to compute the machine path. In this computation, the software considers the set parameters as well as the number of degrees of freedom the selected machine has. With the machine path computed, we can see the machine path represented by the blue line in the plot, with the green points being the filtered points. If we select the full path plot option, we can see the designed material path together with the machine path. For the production of more complex geometries or build-up profiles, bridging of the material during winding can be checked in the bridging plots. With the machine path set, we can start to convert these machine paths into machine trajectories, which are the movements specifically for the specified machine. We can start by opening the trajectory configuration panel, where we can see 4 sections where we can set the configuration parameters. In the winding position section, we can set the position of our tool relative to the product. For this demonstration, I will wind at an angle of 0 degrees with a positive axis rotation direction, and we will wind non-tangent to the surface. In the plot area, we can see a visualization of the specified winding position. In the tool orientation section, we can set the allowed orientations of the tool itself. In here, we can either completely disable a tool orientation or we can limit certain orientations. For now, I will set the tool yaw orientation to 180 degrees. The same goes for the extra axis, which on this tool is the twist axis on the payout part of the tool. For now, I will turn off the payout twist orientation by deselecting the tick box. Since the selected robot is on the track, we can specify the track parameters in the track section. The offset value will give the robot an offset from its neutral position. For this demonstration, I will set the offset to -500. In the negative and positive swing directions, we can allow the robot to swing out of its neutral position. If swing is set to 0, all the actual movement, or the movement along the z-axis, will come from the track. Allowing for swing usually results in smoother production. For this demonstration, I will set both negative and positive swing to 500. With all these settings set, we can set them by pressing the OK button. Now we can convert the filtered machine path points into trajectory points by pressing the Compute button. In the plot, we can see the trajectory points where the TCP would move along. If we select the suspended tape plot, we can see the paths the material would make between the mandrel and the TCP during winding on all the trajectory points. Setting parameters and computing the machine paths and trajectories can be done either for one layer at a time by selecting the layer node, or for the entire product at once by selecting the product node. In the last computation, I used the machine path point filter. If we go back to the machine path parameters and deselect the apply point filtering tick box, we can recompute the machine path without point filtering. This results in just a blue machine path line without the filtered points as green dots. If we now reopen the trajectory configuration panel, we can see that we can now also set filter accuracy settings. With these parameters, the accuracy of the trajectory filtering can be set. The trajectory can be filtered such that less programmed points are sent to the machine. The removal of these trajectory points keeps the accuracy within the specified limits. These limit filter settings can be set in the filter accuracy section. With these parameters properly filled in, we can set them to the layer by pressing the OK button. Now we can compute the trajectory points by pressing the trajectory compute button. With the trajectory points computed, we can again see them visualized in the plot. For the difference between machine path filtering and trajectory filtering, it can be said that the machine path filtering reduces the path resolution by keeping equally spaced points, while trajectory filtering is keeping only the points needed to keep filtered trajectories as close as possible to the original one within the set accuracy. For this demonstration, I will be using the machine path filtering previously shown. With the trajectory points computed, we can run a collision check by pressing the detection button in the collision section of the production tab. During the collision check, it is checked whether the tool collides with the mandrel and whether all points can be reached by the machine. The check runs for all of the layers in the product. For these trajectory points, we can see that there would be collisions in the layers 1 and 3. If we now move to the simulation panel, in the analysis tab, we can simulate the computed production. In this simulation, we can see in which points the collision or singularities would happen. For collisions, we can see that the tool lights up red, indicating a collision at the specific point. We can now resolve this collision by, for example, increasing the winding distance of the layers or by limiting tool orientations. If we now restrict the yaw axis of the tool and allow full twist orientation on the payout axis, we can recompute the trajectories. With the trajectories recomputed, we can rerun the collision detection, which now returns the user message that there are no collisions found. If we now again open the simulation panel, we can simulate the production and see there are no collisions anymore. This means that we can press the Generate Files button in the Machine Files section of the Production tab to generate the machine files. For this file generation, the post-processor in the machine definition is used. This is explained into more depth in the robotic machine definition video. If we would now want to change the machine we are using to produce this product, this can be simply done by clicking the Select Machine button in the Production section of the Production tab. Now we can select another machine we want to use for the production. I will select the non-stationary user frame machine, which is a machine where the robot will hold the mandrel and the material payout point will be stationary. With this machine selected, we can set the actual offset to be 1000. We can set the machine path parameters and compute them. After this, we can also set the trajectory configurations, where we will again limit the yaw to 45 degrees and allow for full twist on the payout axis. Now we can compute the trajectories, and when all of the paths have trajectories, we can run the collision detection. With the collision detection run, we can check the production simulation. If everything looks like we want it to be, we can again generate the production files and move to production. This is the end of the TaniqWind Pro robotic production demonstration video, where I've demonstrated how to set up production using a robot in TaniqWind Pro. If you're interested in other highlighted feature videos, these can be found at the Taniq YouTube channel.